Quantum mechanics powers our modern world, the physics for smartphones, computers, and lasers. Yet physicists have no agreement on what the underlying math actually describes. The math itself is consistent. The Schrödinger equation tracks a quantum system as a wave moving smoothly and deterministically over time. This wave represents multiple possible states at once, a concept known as superposition. As it unfolds, these possibilities overlap without interference. As long as the system remains unobserved, it obeys this continuous, unbroken flow. The mathematics are perfectly predictable. According to the orthodox Copenhagen interpretation, the moment we measure the system, that smooth evolution stops. The wavefunction collapses into a single definite outcome. This is the core of the Schrödinger's cat thought experiment. The cat occupies a state of being both alive and dead until the box is opened, forcing reality to choose. This collapse is instantaneous, discontinuous, and irreversible. It represents a hard break from the smooth mathematical evolution that came before it. This forces us to treat the observer as a distinguished entity, something separate from the physical system that doesn't obey the standard wave-like rules. The collapse rule acts as an artificial patch, added to the equations to ensure the math matches our everyday human experience. In 1957, Hugh Everett III proposed a radical alternative. He argued that we should discard the collapse rule entirely and take the math of the wave function literally. Everett proposed that when an observer measures a system, they become entangled with it. Instead of a collapse, the universe branches, creating separate realities for every possible outcome. We do not feel the universe splitting because of a mechanism called decoherence, a process refined by physicists like Wojciech Zurek. Think of a drop of dye hitting the ocean. The quantum information from the system rapidly leaks out and scatters into the countless degrees of freedom in the surrounding environment. As the environment interacts with the system, the off-diagonal elements of its density matrix decay to zero. This renders the different branches physically orthogonal, making them unable to interact or interfere. The split into parallel worlds emerges as a localized physical process, driven entirely by interactions with the environment. Removing the collapse rule addresses the discontinuity of measurement, but it creates a crisis regarding the origin of probability. If every possible outcome happens with total certainty on its own branch, it is difficult to explain why we experience specific probabilities in our world. When one branch has a massive amplitude and another is tiny, there is no obvious reason why we should expect to find ourselves on the larger one more often. Unless the theory can explain how these different amplitudes translate into the frequencies we observe in experiments, it fails to describe our reality. Physicists Sean Carroll and Charles Stebbins suggest the answer lies in a state called self-locating uncertainty. They focus on the fleeting microsecond after a measurement has occurred, once the universe has already branched, but before the observer registers the result. In this moment, the observer is duplicated. Every atom of their body and every record in their memory is copied across separate tracks of reality, creating multiple versions of themselves. At this step, an observer could know the exact state of the entire universe, yet still be uncertain about which specific branch they are on. In this framework, probability becomes a measure of the observer's ignorance about their own location in the multiverse. To move beyond pure theory, scientists have looked for observational evidence of other universes. One hypothesis suggests that our universe might have collided with neighboring bubble universes in the distant past. Scientists analyzed early cosmic data from the WMAP satellite, searching for temperature anomalies, or bruises, left behind by these hypothetical collisions. A more rigorous follow-up analysis using higher resolution data from the Planck satellite did not reveal any statistically significant evidence of these cosmic scars. The many worlds interpretation remains a consistent mathematical framework, yet it lacks direct observational proof. This lack of proof has led skeptics like Sabine Hossenfelder to question if the theory even qualifies as science. Under the standard of empirical falsifiability, a theory must be capable of being disproven. Without the ability to observe other branches, the multiverse remains a mathematical hypothesis. Proponents argue these branches are simply the logical consequence of the Schrödinger equation. To them, removing the arbitrary collapse rule is the most honest way to do physics. This leaves a choice between two views of reality. We can accept a single world governed by random, unexplained collapses that favor the observer, or we can accept a reality where the math never stops, constantly copying you into innumerable versions of yourself across a fractured multiverse.